Welcome to this webinar. It's great to see a good number of people coming in to learn about direct rainfall methods in Flood Modeler. It's quite a well-timed webinar if any of you caught the thunderstorms that tracked across the UK last night. This webinar will be a combination of presentation and a hands-on demo with the software to show you how you can apply rainfall within the software. In this webinar, I'll be talking you through what direct rainfall modeling is and when it can be used. I'll show you how to construct a direct rainfall model, first off by calculating design rainfall. So by design rainfall, I mean what is the 1 in 100 year, the 1 in 1,000 year rainfall, and how do I calculate that? How to apply that to a 2D model, so what the components of that model are and how to apply it within the model. And then lastly, how to understand the results. With direct rainfall models, there's a bit more processing required to understand the resultant flood risk, and I'll talk you through that. At the end of the session, we've got some time for questions. So as Chris says, if you have any questions, please put them in the question interface on the webinar, and we'll come to those at the end of the talk. First up, what is direct rainfall modeling and when should I use it? So pluvial flooding is caused by intense rainfall. So when we talk about pluvial flooding, we're talking about an intense rainfall event which has overwhelmed the local sewage system or drainage system, resulting in water ponding on the surface and ultimately mobilizing over land and causing flooding. On the right-hand side, we've got two examples. The first photograph is from last night where I live, showing the torrential downpour and flooding on the road. And the other one is from last summer, from a summer fete, of course, showing flooding caused by an intense rainfall event. There are some 3.5 million properties at risk of pluvial surface water flooding in England alone. That's more than at risk from both coastal and river flooding. This continues to increase, so climate change will make this issue worse. Climate change results in global warming, atmospheric warming. That warmer atmosphere is more energetic, so it can hold more moisture, more water, and when it rains, when that water comes down, it can be in greater volumes and more intense. So as climate change progresses, we're likely to see more intense rainfall and more frequent rainfall, and we've seen some very intense rainfall events over the UK over the last few years. When we come to assess the risk associated with that direct rainfall, using a rain on grid or direct rainfall model approach is really useful. So this is where we build a 2D model, a surface model using, say, some sort of ground grid to represent the elevations, apply rainfall directly to it and see where the water runs off to. So we can look at areas of ponding, mobilization and high risk. These models can range from very simple setups using freely available data, and that's what I'll demonstrate a bit later on in this presentation. But we can make them more complex. We can add additional details, so we can start to pull in things like subsurface pipe networks, sewers, linking to other sources of risk such as rivers, coastal, and such like. So these models are very powerful. They can be set up very quickly, and they can allow us to assess the risk of flooding over at small scale or very large scale. When we come to set these up, the most important factor to consider is the rainfall we're applying. What are our estimates of rainfall? So I'll talk a little bit about that to start with. The Flood Estimation Handbook, the FEH, was released in 1999, and this introduced in Volume 2 the concept of a depth, duration, frequency rainfall model. And these are still with us, and they are the preferred method of estimating extreme rainfall for the UK. So a DDF model allows you to calculate a depth of rainfall for a given duration of storm, so 1 hour, 2 hours, 3 hours, 100 hours, and for a given frequency. And by frequency, you can substitute rarity, so how extreme was that event. On the top right-hand corner, I've got an example of a series of DDF curves from FEH. And what you can see on the vertical axes, you've got the depth of rainfall in millimeters. Along the horizontal axes, you've got the duration of that storm in hours. And then you've got a series of curves. And each of these curves are the rarity of the event, from a 1 in 10 year event through to a 1 in 500 year event. And to get the rainfall depth, you simply trace along the desired curve to the given storm duration and track back to get a depth of rainfall. So this provides you with a rainfall depth for a selected duration and rarity of storm. The original FEH work was updated in FEH 13 and again in FEH 22 to take account of the most recent data available. So it's great this data set's been kept up to date, drawing in more and more gauge data, longer records, and particularly with FEH 22, a lot of effort was put into improving the quality of the data in the analysis. This is an image in the FEH 22 technical report comparing for a 1 in 200 year 1 hour storm, the differences between the FEH 22 and the FEH 13 model. And you can see very significant changes between those two models, largely by improving the data quality. So you can see anything from a 40% reduction to a 25% increase in extreme rainfall estimates for this particular example in that data set. And this just demonstrates the importance of using the most up-to-date data, so you're not over or underestimating the intensity of rain you're likely to be applying to your models. In order to undertake this analysis, you need the FEH data, the catchment descriptors. They're generally available from one of two places. UKCH published these on the National River Flow Archive website for gauged stations. So anywhere you've got a UK peak flow gauging station, you can get hold of those catchment descriptors. They're also available for any site in the UK via the FEH web service. That's a paid-for web portal provided by UKCH where you can download site-specific catchment descriptors. Just have a quick look at that. This is what the FEH web service looks like, and this is where I've looked at an individual catchment to get those depth duration curves. So you choose your catchment and then you can click on this rainfall modeling button on the left hand side, and that opens up the rainfall modeling tool. In here, I'm able to choose rainfall modeling either on a catchment scale, so looking at the whole catchment, in this case quite a small one, 63 square kilometers, or a point location depending on what sort of analysis you're undertaking. You can choose the rainfall model you want to apply, so whether that's FEH 13, FEH 22, or the original FEH 1999 rainfall model. You can plug in your storm duration in hours, your return period, click go, and the software will calculate the depth of rainfall you're likely to receive. You can also reverse engineer this as well. So event rarity tool allows you to put a depth and duration in, and the software will work out the rarity of that event. So if you're looking at a historic event, you can start to think about how extreme that event was. You don't need to calculate the rainfall depths within the web service, but the web service does provide you the data you need, those DDF parameters, in order to undertake your analysis. As well as the depth of rainfall, we need a few other things in order to calculate a boundary for our model. So we get a depth, which is in millimeters, but we want to convert that to hyetograph. The hyetograph is the sort of the time varying rainfall during a storm. So there's an example of that on the right-hand side. To do this, we need to consider a few things. First off is the rainfall profile. In the UK, we have two rainfall profiles we use, idealized profiles. We've got the winter one, which is on the top right-hand corner here, and you can see that's a usually quite a shallow hyetograph with a lower peak. And then we have a summer profile, which has a far higher peak. So that reflects those intense convective storms, thunderstorms we often see during the summer months. So depending on your catchment, you choose a different storm profile. For urban catchments, we're usually choosing a summer profile. For rural catchments, which usually have a longer time of concentration, we pick a winter profile. And all these are built into the software, which I'll demonstrate in a few moments. We also need to consider the critical storm duration. So different catchments have different critical storm durations. That's the storm which causes the most flood risk. You can imagine if you're looking at a large rural catchment, several hundred square kilometers, it's going to be a long storm that's going to cause the greatest flood because it takes time for that water to accumulate and peak within the system. For pluvial flood risk, surface water flood risk, we're generally looking at urban locations where it's far more likely that the short storm duration will be impactful. So we're looking at half an hour to an hour storm durations. The other thing we need to consider are losses. So all that rainfall doesn't end up causing flooding. There are two principal losses when we're considering rainfall. The first is losses to the ground, so infiltration. So this is when rain hits the ground and soaks away into the subsurface. And you can imagine that's quite variable, how much water is lost to infiltration. If you're on rains falling on a sort of cracked or fractured limestone, it's going to be highly permeable, and a lot of that water can be lost straight to groundwater. Whereas if you're on an urban area where you've got a lot of hard standing, there's going to be very little infiltration. That water's going to hit the surface and run straight off. We also have losses to drainage networks. So where we've got a formal drainage network, so we've got highway drainage or sewer systems, a loss of water will be moved quickly into that network and taken out of the catchment and removed as a source of risk. We can consider these in a number of different ways. The simplest method, which I'll use in my demonstration, is to apply a loss method. So on that height graph on the right hand side, the dark blue shape is the rainfall from the gross rainfall. So that's the as calculated rainfall profile from FEH. And the light blue is the net rainfall. So I've deducted from that an allowance for losses. And those losses are both into the soil, so infiltration to the ground, and infiltration into the sewer network. We can make an allowance for that, knowing roughly what the conveyance of a sewer network's like. And then you apply that net rainfall directly onto your model. A more complex way of doing it is to include surface infiltration. So within our 2D models, you can use various methods to allow the model to take water off the surface and infiltrate into the ground. And that can be spatially varying. So you can have different infiltration rates for different areas of your model. So if you've got an area which is highly permeable, the water will disappear very quickly. If you've got a paved area, that will be a lot slower. And with these infiltration rates, you can include sewer systems as well. So you can make an allowance for how much water will disappear into the sewer network. And that's a really nice way of doing it. So the rain falls on the ground and a percentage of that is infiltrated and lost from the system. If you want to do something a bit more complex, we can explicitly represent the drainage network. So if we've got a subsurface pipe network, we can build that into our model in Flood Modeler using the 1D urban component. So we can model those individual pipes and the connectivity, so water will fall on the ground, flow into the drainage network, and then be taken away out of the system. And depending on what your study is trying to achieve, these are the sort of the broad three approaches. Once we've got our rainfall, we need to then apply it to a 2D model. And I'm going to show you a demonstration of a simple 2D model I built using open source data and what data is required. So to build our model, we need some digital elevation data, DEM data. In this case, I'm using LiDAR, which I've downloaded from the DEFRA website. So this is freely available, high resolution LiDAR for the whole of England from the DEFRA website. You can get similar data for Scotland, Wales, and Northern Ireland as well. And that provides the elevation of my model where the water is going to run. I'm also using some land use data, and this is to assign roughnesses to the land and also model key features like buildings and roads. I've sourced this from two places. I've used OpenStreetMap or OSM data to provide me my buildings, and I'll talk a bit more about that in a second. And I've used OpenOS, so Ordnance Survey Open Data, to provide my road network. Both these are open source data sets, so they're freely available, and you can bring that data easily into your system. In the case of the buildings in this model, I've elevated them. So buildings tend to have a threshold. So I've raised the area under my buildings by 200 mil. And for the roads, I've depressed them by 200 mil to make them the preferential flow paths within my model. In addition to the model data, I need those boundary conditions, and that's the rainfall data I've calculated previously. And I also need to account for interaction with other sources of flooding, so sewers, rivers, coastal. And I've talked about some ways of modeling those on the previous slide. On the right hand side, you can see my basic model setup. So I've got the area I'm modeling, which is a place called Upton upon Severn. You can see the road network in red, and you can see the buildings in green superimposed. And I can also drop the LiDAR on top, so you can see the elevation, the profile of that location. So Upton's quite a raised area in a low floodplain, so there's quite high elevations around Upton and lots of places for the water to move around. Before I jump into my model, I just want to say a word on data quality. I mentioned I grabbed the buildings from OpenStreetMap. That's a fantastic resource with global mapping, which is all community driven, but you do need to be aware of some limitations with it. So the green boxes on this slide show the building locations, and underneath I've got Ordnance Survey vector map data. This is the freely available data from OS, which you can also use for the building layer. And you can see the differences in the building representations between OSM and OS vector map. There's different shapes to those buildings, and quite a few buildings are missing from the OSM data, so they need to be added in. If I look in a bit more detail and bring in some paid for data, this is Ordnance Survey master map data, which is data you need to pay to access. And you can see there's a lot of discrepancy there between the OSM data and the Ordnance Survey data. There's a lot more buildings, particularly in the top left-hand corner, which haven't been captured. And also the shapes of the buildings aren't as they are in reality. So the OS master map really is the highest quality land use data you're going to get for the UK. And it just shows although you can build these models with freely available open data, you need to be aware of what some of the limitations are and always review it to make sure it's sufficiently accurate, and consider buying other data sources if necessary. So into a live demonstration. Here's one I built earlier. Switch off that urban model. So the place I'm looking at is Upton upon Severn. This is Flood Modeler, and what I've done is I've dropped some background mapping on here. This is OpenStreetMap, but I can switch that to other data types. For instance, I can look at some satellite mapping or the OS vector map data I was showing you earlier. I'll stick with the OSM data. This is the area I want to model, and so I need my input data sets. So I've got my my building layer, I've got my roads layer, and I've got my LiDAR, which I've previously downloaded and brought into Flood Modeler. I also need to define an active area. This is the area over which I'll be building my model. So that's simply a polygon I've drawn in Flood Modeler. So under the 2D build option, I've got this active area button, and I've just drawn the area I want to model. This is so I constrain my study to the area I'm interested in, and my model's not too big, and so won't take too long to run. So I've got all the components for my physical model, but I do need to create my rainfall, and I'll show you how to do that in Flood Modeler. So this is 7.1 of Flood Modeler, which was released a few weeks ago. And as part of that, we've got the Enhanced Hydrology Plus module. Within here, I can calculate my rainfall, all my flow for my rivers, and do a lot of other things. So the first thing I'll do is look at my catchments. So if I click this button here, I can see where I've got purchased catchment data from FEH online. So I've got lots of these data points around the UK, but the one I'm interested in is this one here. This is just one I had purchased already. If I was looking at Upton in detail, I'd probably want to consider additional catchments in and around Upton to make sure I've got the most representative rainfall data available. But for this example, it's fine to use this local data. What I need to do is calculate the rainfall at this point. So I'm going to click on these catchment descriptors, and I'm going to create a calculation point. It's going to be my rainfall data. Click OK. And I've got this little calculation point has popped up. Now that's there, I can go into those calculation point properties, and I can start to calculate my rainfall to apply to my model. I can look at my catchment descriptors in here, and I can amend them if I want to. I'm going to leave these as default. There was a webinar last week where I talked about how you can edit these and change these. What I'm interested in is RFH. This is a piece of software from Wallingford Hydro Solutions, which is linked to Flood Modeler, that allows you to calculate your rainfall profiles. I click Initiate New Analysis, and RFH will open up, just taking a second to load as it grabs a license. Here we go. Pull that across. I'm not going to talk in detail about how to use this software. There's a lot of detail on the Wallingford Hydro Solutions website, but I'm just going to touch on a few bits. So in here, I can choose the return periods I'm interested in, and also the storm durations I'm interested in. So in this case, I'm going to change that to 5.5 hours. I'm going to set my time step to 00:30. Apply. So I've created quite a short storm duration. I've specified that, and you can see these height graphs being produced by the software. And I can see I've chosen the FEH22 model. I've got a load of options on the next page to consider losses, urbanisation, so on. I'm going to leave these as default for this example, but I'd do this in a lot more detail if I was doing a true study. Click Save, and that sends the data back to Flood Modeler. See, it's imported that data. Click OK, and I can see that's brought those results into Flood Modeler for me. So I've got all those different return period results available to me, including the height graphs, both for gross and net, so with the losses reduced. I'm now going to export those out as a CSV file and just save those there. And I can then use them when I build my model. So I build my model, just create a new model really quickly. To build the model is incredibly easy in Flood Modeler. I just set a start end time, say run it for 10 hours. I build my domain by dragging and dropping my components in here, my active area in there, my buildings and my roads. I've obviously set these up as I want them. I'll use a default Manning's value for now, and I'd go back and refine that later. And the key thing I need to do is add my rainfall. So I simply click Add. I choose an area over I want to apply that rainfall. So I'm going to use the 2 seconds. Active area again. So I'm going to apply the rainfall over my active area. And I need to apply that rainfall file I exported a few minutes ago. And I'm going to apply that urban one. And what I can do is I can choose the rarity event I want to apply. So all those events I looked at, I can simply choose one I want to apply. I can also choose which model I want to apply. So I can apply the gross rainfall, or I can apply the net rainfall. So obviously the net rainfall is the more appropriate one. Click OK. Software's just checking I want to run in double precision, which is always a good idea for a rainfall boundary. And that's the model built. And I click Run and it will run through. It's quite a big model, so it will take a few hours to run through. So I'm going to go to one I produced earlier. So this one here. I'm going to load in the time series data, and I'm just going to bring in the maximum results. I'll talk on the next slide about why I'm doing that. This all looks very blue because what's happened here is every cell in the model gets wet when it rains. So I'm just going to quickly tweak the color ramp of this so it looks a bit more sensible. So I'm going to hide any shallow depths. I'm going to do that and that. So I really want to, there we go, filter out the shallow. So when it rains, you get a very shallow depth of flooding on every single cell. I've just filtered those out. So you only see where you've got deep accumulations of water, and anything very deep, so in this case, a meter plus, you're seeing as red. So it really draws your eye to where you've got risk. And I can switch this to show the satellite data. So it's a lot more obvious where you've got those areas of high risk within your model. And it's very quick and easy to pull these together. Jumping back to my presentation, these are some of the outputs we get from the model. So we can see the rainfall inputs to my hydraulic model and the growing volume of water in my model as the simulation runs, so I can check it's worked properly. And as I was saying earlier, when a direct rainfall model, it's important to change how you visualize the results. So by default, you'll see all the cells wet because they've all got a very shallow depth of water, a few mil in them. But we can adjust the color ramp such that you show only areas with deep water, and then you can refine that so you can see areas of deepest water in particular colors, which aids with your analysis. So you can see areas of high velocity, high hazard, or deep water, and according to your analysis. And they're quite nice and easy to visualize, and you get a good idea of what the risk is in different areas. That's pretty much it. So I'm just going to quickly summarize. Extreme rainfall is a major source of flood risk to the UK, with 3.5 million properties at risk in England alone. The best methods available to assess extreme rainfall are the FEH methods, which were introduced in 1999 and have continued to be improved. 2D direct rainfall models are a key tool for evaluating that risk, and I've shown you how simply you can build a model using openly available data, but you should always be aware of the limitations of your input data and the limitations when you're deciding how to set your model up and how complex to make it. Those more complex models can include other aspects like drainage networks, multiple sources of flooding, and infiltration as required.